It seemed like this was the only, is this like the only remote lecture for you this semester? These chemistry lectures. Or do you have something else remote? Yeah, because this looked like this is the only one for this today. So maybe people are doing something else. But I will be talking here for the next, I even booked the whole slot of 2 hours in case it takes that long time. And I'm of course recording this. And should I have my head somehow there? Well, sometimes it appears for sure and sometimes not. Can you find a course in Moodle? Can you access the course?
I don't have it on Moodle yet.
Okay, so can you, if you try, can you find this course if you look for it or is there some problem with that? Because the way it's done, you should be able to access it now. That's, when I like press some button in the Peppi, then this should be in your Moodle. And I have pressed that button.
Okay, I found it.
Okay, great. Okay, so then that's also sorted. So then everybody should be able to find a course. And here is some information, whatever. I can go through the information then. I have some kind of slideshow for that. Share. That. Mm-hmm. Oh, there's the schedule. Yeah, what is okay. So chemistry course. Wow. Full 3 credits. Third and fourth periods. Okay. Remote and face-to-face lectures. as well as face-to-face calculation exercises. So this is done the same way as the Finnish courses go. So we have remote and face-to-face because it's the same way, and it was because of the Finnish students' schedule demands. And then when I was being asked how I want to do the course in English like a year ago, then I said, okay, it can be the same because I didn't really know. So it's going exactly the same way as the chemistry course in Finnish. Theory lessons are also recorded. Yeah, well, I guess I will be still recording all the lessons like I have been doing this year for maybe that's the best to continue the same way. The exam is at the end of the course and it's a paper exam and the retake is an examinarium, just like in the maths. The same old story. Students' use of time, I guess we have about 28 lessons. The exam should take only 2 hours. So it's this kind of a bit like small exam, like in the maths independent study. Yeah, because you would need to, for 3 credit course, the time use calculated is about 81 hours. Well, it might not be that much, but it depends, of course, on the background. Topics of the course are, there's quite a wide variety of topics, and there should still be one more, but not, at least not this year. So we have elements and the periodic table, chemical formula, amount of substance, chemical reactions, physical states of matter and mixtures, acids and bases, electrochemistry, combustion and flue gases, and chemistry and the circular economy. So all this we should get through at least, some of it, like, of course, we can't go really deeply into any subject. The schedule is here, but this might change still a bit. So now at least on this, we were supposed to have this introduction earlier, but I was sick. And then now we have the first lecture already. And these are the topics for the first lecture. So elements, periodic table, chemical bonding, oxidation numbers, amount of substance, and stoichiometry. Quite a lot. And then we have exercises. Then again, a remote lecture and exercises. And also on the next exercise time, which would be almost in a month, that's the 10th of the February, we would need to have elementary presentations. So you would need to make a little presentation of an element that you've chosen, but we can agree on this in the next week's lesson when we actually meet to do the exercises. Then we would continue with the acids and bases, and then we would also need the exercises. So because we have the presentations, we have to share the exercises to 2 lessons. So from the chemical reaction and acids and bases, it goes a bit weird way. Then combustion and flue gases. So then we have everything on, like, being present. And most probably for this part, there will be some changes because there's still one topic missing, which is the physical states of matter and mixtures. And it looks like we're getting also this teaching practitioner called Mianur Rahman, and she's a senior chemist in the Optitune company, and she's also doing teaching practice, but I didn't meet her yet. I was supposed to meet her as well, but I got sick. And we will meet next week and agree which parts she teaches, but at least she's obviously very experienced person in the chemistry, and she will do lessons that are in the classroom for sure. And it would be great if people would be present there as well when she's there. So because there's only 6 of you participating on the course, so especially when she's there, you should be there. Of course, to make your presentation, you should be present as well. Yeah, it's it's good to be present if that's possible. Then we have exam. Yeah, the paper exam. And we have also these little, exercises again, assignments, These must be completed during the duration of the course. The element presentation, which is compulsory as well. And you get 12 points in total. And then the grades, I think the next, no, I didn't put it there. Yeah, here. Okay. Exam 24, you have to get the third of the points at least. Presentation, yeah, so you at least have to make it. If you didn't appear to present it, okay, then you lose 6 points. Little quizzes, and then in total you can get 48 points, and then you get the grading scale comes from there. And we'll see if this, this is again like first time, so it might change, but at least now it looks reasonable like this. Of course, it depends also on the other teacher of the course, the Janur, if she thinks that she wants to put something here. But I'll see. I don't know yet. Some kind of exercises or something. Okay, so I think here is mainly what I will start covering now. This is just a presentation, like about I will cover those things in my other presentation. Let's go quickly there. So what we are supposed to now get to know about is just very, how we got the matter, what it consists of, what is there in the smallest particle of matter or even smaller ones, the atom, and then how we can organize the elements, depending what kind of atoms they have in the periodic table. And basically what is there, what you can find from there, how you can then make groups of and then you can also make periods of the elements, and how you can sort them out, metals, non-metals, for example, how you calculate the amount of substance and molar masses, and yeah, basically the amount of substance calculations, the simple ones. Chemical bonds, yeah, how the elements form chemical bonds with each other to form other kind of substances then. And then chemical reactions, but this is the next topic, so not on this lesson. Simple chemical reactions, how you calculate from the chemical formulas of the reactions, the amount that you need there, the reactants, or how much you get the product. What kind of chemical reactions you can have. You have the law of conservation of mass. It's neither created nor destroyed in the chemical reaction, so that's how you can base the chemical reaction equations and calculate the amount. What kind of chemical reactions you have? Exothermic, endothermic. Combustion is important on this course, and the calculations with that, what you get from the combustion reaction as products. Here, for example, a combustion reaction of methane. And while with complete combustion, you produce the carbon dioxide and water. This is something that you might have heard before. Yeah, here is the balancing chemical equations. This is very important in chemistry to balance the chemical reactions. So you have to calculate that you didn't lose anything in the reaction, and you have the same amount of all the elements on both sides, basically. This is something that we'll be practicing in the first exercises, calculation exercises, among other things. So you have to put some kind of multipliers if it happened that you didn't have the same amount immediately when you wrote the equation. Acids and bases. Acid donates the H plus or proton, and base receives. pH value measures the acidity or alkalinity of a solution. These are most probably familiar concepts to you as well, but we will be calculating that kind of calculations as well. Physical states of matter. Well, okay. This you have been talking about for sure in physics already. Solid, liquid, gas. Well, plasma. I think we stick mainly with this. Three forms: solid, liquid, and gas. And how, yeah. This is, I think, the first subject that the Mianur will be teaching you. At least that's what we agreed for now. Physical states of matter and mixtures, and how you can well, classify them: homogeneous, heterogeneous. You know, substances are physically but not chemically combined. So don't have mixed composition or chemical bonding between components. So these things we will have the different teacher teaching you at some point, but I'm not completely sure when in the schedule yet. I have to agree with her. And there's many types of mixtures, colloids. For sure, you heard about these things earlier. And then the separation methods, and I think that all of you will be going to the laboratory later on. You have another course of chemistry where you will be then practicing these separation methods: filtration, distillation, evaporation, and chromatography. I don't need to maybe tell more about those now. Oh, okay. The acids and bases. There was already one slide about this. The pH, you know the colors. You've been using some pH meter or pH paper in school. At least you can measure the acidity or alkalinity of the solution. And the neutralization, especially for an engineer, is important. If you get some kind of a discharge that is acid, or you have to neutralize it. Put enough base there, then you get salt and water. And we have some calculations with this, I think, as well. Oh, what are strong acids and bases, and then also the weak ones. Okay, then the oxidation reduction. Electrons are transferred from atom to another. In oxidations, you donate, and reducing is receiving. And this is to do with the electrochemistry. Okay, this is some in Finnish. Sorry about that. But iron oxidizes when it rusts. You have anode and cathode. Most probably you're familiar with these concepts as well. And for example, you can have copper ions being produced if you have a right kind of a pair, and if you provide current or then you can get current. You can make a battery or galvanic cells, chemical energy into electrical energy, battery or electrolysis, use electrical energy to produce chemical reaction, and you, for example, break water into hydrogen and oxygen there. And rusting of metal is oxidation reduction reaction. And you have this series, electrochemical series of the metals where you can check what happens when you put them as anode and cathode in the reactions. So electrochemistry is the study of chemical reactions in which electrical energy is generated or consumed. And oxidation and reduction reactions are central there. Okay. And then there are the galvanic cell, electrolytic cell. We'll talk about this later. So galvanic cells is spontaneous electrolytic. You need to use electrical energy. Okay, this is the same. And there are different types of, batteries. This is a big field for sure for you in the practical applications then. Combustion and flue gases. Well, in combustion, oxygen is reacting with some substance. You release heat and light. And you produce carbon dioxide and water, or if you have incomplete combustion, you produce carbon monoxide. And flue gases are exhaust gases from combustion, and managing the emissions is important. And to know that we will do calculations where we calculate the what kind of flue gases you get out of certain combustion reactions. And then we have also the chemistry and circular economy, green transition in chemistry. Well, we'll be hoping for that. Transition towards more sustainable and environmentally friendly chemical processes and products. And we should, of course, reduce environmental impacts, improve resource efficiency. Principles of green chemistry, for sure, you heard about these. I'm not gonna read them through now. And well, where you use this, you should use it, of course, everywhere. Renewable energy, solar, wind power, hydrogen economy, hydrogen as energy source. You have been already, I heard, producing hydrogen in some kind of lab experiment. Recycling and reuse of materials and chemicals. Of course, there's challenges in the future, and this is what you're studying now. It's your field. Significant investment, financial resources, collaboration, new innovation, and close cooperation between companies and universities. At least now we get a company representative even teaching us chemistry on this course, which is great. So we aim to reduce waste, reuse materials. And this is a key role in recycling, material recovery, and sustainable production. And there's many examples, of course. Waste to energy processes. So what then, what all we learned on the course? First, the periodic table, how to quantify matter using the mole concept. Identify and writing chemical reactions, understanding mixtures and how to separate them. Well, maybe this is how to separate them, maybe in theory a little bit, and then later in the practice. Properties and reactions of acids and bases, basics of electrochemistry and redox reactions, chemistry behind combustion and flue gases, and the role of chemistry in sustainable circular economy. This is quite a lot for 3 credit course to obtain. So there's quite a lot of content on this course. Okay, so let's go then. Who is here? Two more. Hello. Do you have anything to ask now, or do I just continue about the you found the course in the Moodle yet? Both of you? Maybe you're still awake. And now I should be talking more about the basics of chemistry. So, but you can ask if you have something in between then. Okay? Okay, so then the next topic, or first topic, because the actually first topic was now to introduce the whole course. And then we can talk about that more also when we meet next week, how the course is carried out, if you don't want to ask now, and there's only 2 of you anyway. Okay, so I will be talking now about just the really basics: structure of the atom, periodic table, chemical bonding. Oops. Yeah, the Big Bang. Okay, so we have the Big Bang theory, and that explains the origin of the universe and origin of the matter. And according to that theory, that was 13.8 billion years ago. And that initiated the expansion of the universe that still continues. This is the theory that we mostly trust today. And then the matter started also forming when the Big Bang happened. So first we would get quarks and gluons, and then the quarks combine to form protons and neutrons. And this was during the first seconds of the Big Bang. This is what has been thought that happened. So there happened a nuclear fusion, and some nuclei of light elements were being formed. So of the first elements of our periodic table, hydrogen and helium. But then about 380,000 years after the Big Bang, we would get the atoms. So we would get also electrons joining the nuclei. And over millions of years, then matter began to clump together, forming stars and galaxies. So that's how we roll. So there would be here proton and neutron, then forming some kind of nuclei. This could be called deuterium, because there's proton and also the neutron. So it's usually the hydrogen is only the proton without the neutron, and it can still have another neutron there joining. So that would be then tritium. And then if 2 of these are joined, you get helium, and then the helium core, and you kick 1 neutron out. Here you just get some kind of energy, some kind of radiation. Okay, that's for sure interesting. So this is how we got the light elements. There's some evidence for the Big Bang. We have this Hubble telescope that's observing things in the space and showing that galaxies are moving away from us. Light elements are the most common in the universe anyway. Hydrogen, helium. Also lithium, they match the theoretical predictions of the Big Bang theory. So that's why we could maybe trust it. Okay, sorry about this this table being in Finnish. Hydrogen is the most abundant element. Well, here it says vety, hydrogen. It's, well, about 73%. Here 75, 74, 75. Helium 24% of visible matter. But only small amounts of lithium were produced. But its abundance matches the theoretical predictions. And then, of course, these light elements form the foundation for the creation of heavier elements that were then formed in stellar nuclear fusion reactions and supernova explosions. Okay, here's, oops, more about that. Okay, well, about hydrogen still. So, the most common in the universe, about 73 to 75% of the mass of the universe. And then 90% of the atoms are hydrogen, 9% helium, and 1% only other elements. Sun and the other stars are composed primarily of hydrogen. And it's in sun, in also our sun, that heats us, the hydrogen continuously fuses into helium. And this is, of course, vital reaction for the life on Earth, so that we get the light and the heat. Heat radiation. So, okay, on Earth, the hydrogen is only the 10th most abundant element. So it's a lot rarer than in the universe overall. And it's because it's light, it only accounts for only about 0.9% of the Earth's total mass, and even less in the Earth's crust. And here are some pictures, again, how this tritium and deuterium might form, for example, some kind of helium core, because there is, oh, yes, helium alpha particle. So you kick the neutron out and you get also the energy. So this reaction that's happening in the sun, and the hydrogen atoms are having the fusion reaction into helium, and we get the heat and the light. And this is something that we would like to do also on the Earth and create similar way energy, have the fusion reaction in the power plants, but it's not so easy to form that kind of environment as you have in the core of the sun. Heavier elements, of course, we need those as well. So how were they created? Nuclear fusion reactions inside stars, okay? Supernova explosions. So stars are formed when hydrogen and helium gases collapse together under gravity. But in the core, then there's the nuclear fusion, and light elements fuse in the heavier elements. And then when star uses up its hydrogen reserves, it begins to fuse helium in the heavier elements, like carbon and oxygen. So this is not something that's yet happening in our sun, but of course it's happened in many other stars. This process continues until iron is formed in the star's core, which is the end point of nuclear fusion, as iron is the most stable nucleus energetically. And then, of course, we have also heavier elements than iron. So then in the supernova explosions, you can get heavier elements like gold, uranium, or neutron capture. Yeah, there's also neutron star collisions, extremely heavy elements. Also, here is also platinum and gold mentioned. So there's these ways of getting heavier elements as well that are, of course, crucial for the creation and also distribution of those elements throughout the universe. Oops. Proportion of elements on Earth. Okay, so we have mostly oxygen. Then we have silicon, aluminum, iron. So here is mentioned what we have here, what we have in the on the Earth, in the Earth's crust. There's mostly iron in the core of Earth as well. Okay. Okay. So then let's look at the atom. There's the nucleus. Well, here seems to be two protons, then two neutrons. So the protons have the positive elemental charge, and then the electrons the same amount of elemental charge but negative, and the whole atom is positive from the outside. The core is very small, and then the electrons are usually marked to go round it, a bit like planets around the sun, but this is not completely correct. It's more like a probability, some kind of probability of finding the electron, and it's higher on certain distances from the core. And the electrons go to these distances or the probabilities so that they gain the lowest energy position there. Electron cloud, it could be called. Atom is electrically neutral because it contains always equal number of protons and electrons. And how we figured out that this kind of a thing is, everything consists of things like atoms. Already in the 18th century, people were starting to, have some evidence for this. So some Rutherford was managing to shoot alpha particles, so this is the helium core, to some gold foil. And some bounced back, some went through. So he could figure out that there is something small there, and then something that it can go through as well. The little particle. And it must be this electron cloud where the electron can be sort of wherever. Of course, it has more probability of being in certain places. And the core, very small. And then the whole atom also very small, but most of it is this electron cloud. So even in the atom, being very small, the core is even smaller. Then we have the orbitals, regions around the atom where the electrons are most likely to be found. And they can be classified into different types on their shape and energy level. So at first the electrons would go to the 1s, which is a spherical shape. It can contain maximum of 2 electrons. And then you have the 2s orbital, and then after that the 2p. So the p already looks a bit like more complicated. It's a like form of 8. And the probability of finding electrons are in this kind of shape. And then once there is a need, there will be a d orbital, which is already more complicated, and then the f orbital. The d orbitals are with these transition metals that we can look at that in the element table then soon. And there's many things to do with this, which you can maybe know already about, or then maybe you end up studying more about, but maybe not on this course that much. But the electrons fill up the orbitals so that they would have the lowest energy possible anyway. Okay, so here is an example of an atom that's not now the hydrogen or helium, but carbon. It has 6 protons, a varying amount of neutrons. So the neutrons are there to stabilize the core, but you can have them different amounts, and then you have different isotopes of the substance. Of course, if there's 6 protons, you also have 6 electrons, and they are marked the way here. Now, where's the biggest probability of finding them? Okay, first shell contains 2 electrons, like was said. So there's only the 1s orbital. Second shell contains 4 electrons. And then you can make the electron configuration as well. You can mark it the way where you have the electrons on all the cores, all the electron cores, or then just this outermost core. So the electrons that are like the ones that the carbon uses to form substances with other elements. So for chemical reactions, it uses these 4 ones because it wants 8 actually. So these ones are the ones that are the reactive ones. They are distributed to 2s and 2p orbitals. Carbon is known for its ability to form long chains and rings with other carbon atoms, and it makes it central element in organic chemistry. Organic chemistry is the part that is a bit lacking on this course. Hopefully on the next chemistry course, you have more of it. This is of course very vital for the living matter. Chemistry of living matter is organic chemistry. Okay. So here's still more about elements, and here you can see them already, how they are put into the periodic table. 1s core, helium, hydrogen, helium, and then the lithium. 2s core and beryllium, 2s core, and then 2p starts to fill here. And different elements differ from each other based on the number of protons in their atomic nucleus. and that determines the atomic number of the element. Electron configurations are so the electrons are arranged on the electron shells, and it affects the chemical properties and reactivity of the element. Atomic masses of elements vary because they have different numbers of neutrons in their nucleus. Okay, well, of course, also different numbers of protons. Carbon has an atomic mass about 12 atomic mass units, 12 grams per mole. And uranium has atomic mass of 238, almost 240 grams per mole. So, of course, it's a lot heavier because it has a lot more protons and also neutrons in the core. You can't actually see it in this, but we can see it in the later on. Elements can be metals, non-metals, semi-metals. Their chemical properties vary greatly. Sodium is highly reactive metal. Helium is an inert noble gas. And melting and boiling points, densities, and other physical properties also vary. Well, there's also this metal, mercury, that's liquid at room temperature. Iron is solid. And the periodic table helps to understand and compare the properties of elements and the differences between them. So you can mark the element this way. Mass number would be here in the left corner and atomic number on the right corner. And the symbol of the element is here in the middle. For example, carbon. So it has 6 protons. Number of protons is this atomic number that's in the left corner. And mass number, so the protons and neutrons calculated together, would be then 12. So that means that it has also 6 neutrons. Isotopes, yes. So it refers to atoms of the same element that have the same number of protons, but different number of neutrons. So they have the same atomic number, so they are in the same place in the periodic table, based on the fact that they have, for example, this hydrogen has only one proton and also only one electron. But then it can have these chargeless particles called neutrons, varying amount in the nuclei. And for hydrogen, you can find 3 possible isotopes. So one would be without any neutrons. This is the most common one. Then you can have, that's called protium. And then you can have 1 neutron, that's called deuterium. And then if you have 3, it's tritium. 2, of neutrons. Did I say 2 or 3? Okay. Why are there neutrons in the nucleus anyway? So they are important for the stability of the nucleus. And they help balance the nuclear forces because protons are positively charged and repel each other due to the electromagnetic force. But the neutrons, when you have them there, they have no electrical charge, and it helps to hold the nucleus together. And the number of neutrons can vary in atoms of the same element, and this results in different isotopes. Carbon, for example, has several isotopes, and this carbon-12 that was there as an example is the most common. So you have 6 neutrons. You can also have carbon-14, where you would have 8 neutrons. Radioactivity also, the number of the neutrons affects that. So you can have an unstable nuclei if you have too many or too few neutrons. And then it can decay and release radiation and release the neutrons as well. So the neutrons are central for the stability and chemical properties of the atomic nucleus. Okay, periodic table, or the table of elements. It's a table that groups the known elements according to their electronic structure or how many protons you have in the nuclei, chemical properties. It's the basic tool of chemistry, and it helps to understand how different elements react with each other and what kind of compounds you get. So the vertical rows are groups, and the elements of the same group have similar structure of the outermost electron shell. So the chemical properties then are similar. And the horizontal rows are called periods. And the sequence number of the row tells you how many electron shells the element has. The ones, those shells that are marked, like you would have those electrons there, like the planets going around the sun. Blocks, then you have different kind of blocks. So you can have 4 blocks with the S, orbital, p orbital, d orbital, depending where the outermost electrons are. Sorry, here is some kind of little mistake. There's something in this text. Okay, but anyhow, the S group, you have the outermost electrons are on the S orbital or p. They are on the p orbital or d on the d orbital. These were the transition metals, or the F orbital. That was the most complicated looking thing. How the periodic table was being made is there was this chemist Dmitry Mendeleev, and he has already developed this on the 1800s. And he arranged the known elements by their atomic masses and chemical properties. And he noticed that certain properties repeated at regular intervals. And then he also left there some blank spots. So because he was predicting that new elements would later be discovered that would fit into these spaces. And today we have 118 known elements. And the periodic table is a central tool in chemical research and education. Okay. So here the periodic table of elements. This is not so clear, but anyhow, you can see there the symbol, the atomic number, and then you can also see the atomic weight, and then the electrons per shell. Then we have this also in the technical formulas. Here it's a bit more nice and colorful than there. And then you can see all how the groups are being named, things like this. You can also classify the elements by the formation processes. This is something that I found in Wikipedia, how these elements were being formed. For example, hydrogen. Well, we think all the hydrogen was being formed in the Big Bang fusion. And then helium, yes, well, Big Bang fusion, but then Also, exploding massive stars. Where is this merging of exploding white dwarfs? Dying low mass stars, exploding massive stars. Human synthesis, no stable. Which one of this is actually our sun? Cosmic merging neutron wolf there. Okay, anyhow, there's also some elements that have been synthesized by humans in the laboratory, and these don't obviously exist in the nature or in the universe, or who knows. But there's, for example, exploding massive stars produce all of our oxygen and fluorine, neon, or exploding white dwarfs, most of the mangan, iron, cobalt, merging neutron stars. Then, for example, iodine, dying low mass stars. This must be our sun, dying low mass star. It doesn't die yet, but at some point. So there, it's also producing, for example, helium, lithium. Okay, cosmic ray fission. So there's many ways of the elements being formed, and they can be they can be also classified by that. Then okay, groups. So the groups have the similar chemical properties for chemical reactions, and you can give them names, and they have been given names. So the first would be alkali metals, then you have alkaline earth metals, transition metals. Wow, I don't even know these names in English, but I guess crystallogens, pnictogens, chalcogens, halogens, and noble. These are familiar for me, lanthanides and actinides, but these three sound a bit exotic. But this is how they are named. Periods. Oops. Horizontal rows then. Elements are arranged according to the atomic. Okay, yeah. The sequence number tells how many electron shells you have. Okay, section 1, only hydrogen and helium. Section 2 and 3. Okay, other elements. And then you have section 4 and 5. And then you have the transition metals. So here you're still filling the S and P orbitals, and then here you already are filling the D orbitals, and then for the lanthanides and actinides, the F orbitals with electrons. Within a period, properties of the elements vary a lot, so it's not the same chemical properties at all. Metallic elements are usually at the beginning and non-metals at the end. Blocks. Yes, this was what we were already talking about. S block, S orbital, or P block, P orbital, D block, D orbital, and F block, F orbital. And more about the blocks, there are many pictures of this. And you can even see here now. Here's 1s, 2s, 3s, 2p, 3p. Yeah, and how these orbitals are being filled. So which is the energetically lowest. So for example, here on the fourth period, first you fill 4s and after that 3D. So the 4s to fill it first is more energetically favorable. And here you can see all the elements and their the number of the protons and electrons in the protons in the core, electrons in the neutral atom. Then you can organize them this way as well, or put into groups. So you have the non-metals as blue here, the metals that are red, and metalloids here marked with yellow. So what are the metals then? Elements that share common properties, such as good electrical thermal conductivity, luster, malleability, and they can be divided into this kind of groups: alkali metals, alkaline earth metals. So these are the first two rows in the periodic table. Transition metals, this is the one with the D orbital filling, lanthanides and actinoids with the F orbital filling. They are located on the left side and in the middle of the periodic table, and non-metals on the right side. So the electron structure in metals, metal consists of electron cells around the atomic nucleus where the electrons are located. Okay, well, that's how all the elements are being built. But metals are special. Their outer electrons are relatively loosely attached to the atom, and that allows them to move freely in the chemical, in the metal lattice. So they are sort of sharing, they are good in sharing electrons together. So this would be, for example, magnesium metal, and those outermost electrons, which magnesium has two to share, they would be all there just going around and having a party. And this is how they conduct electricity and heat. Most metals have 1 to 3 outer electrons that they can easily donate and form positive ions and have this kind of shared custody of electrons. Here's natrium, something about it. Well, this is really reactive and you can't really find it pure in the nature. Sodium. Yeah, in English it's called sodium. Okay, that's just an example. Non-metals. So then they don't behave like metals and are usually located on the right side of the periodic table here. And they usually have 4 or more outer electrons. They don't give them to be shared with everybody. So they can be gases like oxygen, and nitrogen, solids like carbon or sulfur. So the key properties, they have poor electrical and thermal conductivity. They don't conduct electricity and heat as well. They form covalent bonds together. So they share electrons in the covalent bonds with each other, but not with everybody, just like the nearby atoms that they have formed a bond with. They can exist in different stages, like gases, liquids, and solids. Okay. There's many examples. Carbon, nitrogen, oxygen. Non-metal bonding. Mainly covalent bonds with each other, the non-metals. So the two non-metal atoms share a pair of electrons a pair or more, and filling the outer electron shell of both atoms and reaching a more stable state, more energetically favorable state. For example, in water, oxygen and hydrogen share electrons to form covalent bonds. And then you can have a polar covalent bond. So the other atom, which in water, for example, would be the oxygen, has a little bit more of the electrons to itself than the hydrogen. And that makes it more negatively charged, and the hydrogen more positively charged. And then this affects on the consistence of water, for example. This is why it's such a unique substance. Or then you can have some covalent bonds where the electronegativity difference is not that big, and they are mainly just like you have the same electrical charge in all of the atoms being there. Nonmetals form ionic bonds with metals. So nonmetal attracts the electrons and it sort of takes them to itself, and the metal donates them. And then you get a positive and negative ions. There's more about that later. Okay, covalent bond examples here with hydrogen. So they share a pair of electrons. That's how they get their electron cell full. And this is a more energetically favorable state. So this is how you find hydrogen as a pure substance in the nature. You find it as a hydrogen gas. Oxygen, so they already share 2 pairs of electrons. This is how they get a full outer shell of electrons, because the full shell here is 8 electrons, and that's a double bond. Nitrogen forms a triple bond, so it already shares 3 pairs of electrons. In water, when the oxygen forms a bond with 2 hydrogens, everybody's happy because oxygen gets 8 electrons on the outer shell, so it's full, and the hydrogen gets 2, so it's full as well. Okay, group names and what kind of groups you have in the periodic table. We should take a little bit more look at this. Let's see, alkali metals. First group in the periodic table. And there's lithium, sodium, and potassium, and so on. Very reactive, especially with water. So they have only 1 electron on the outermost shell. And for them, it's more electrically favorable to get rid of that. So then they would have the full shell of electrons. They want to donate the electron. Reaction of sodium with water, you get the natrium hydroxide. This is commonly used base. Sodium hydroxide, sorry. It's called sodium in English. You don't really find this kind of metals pure in the nature because they are so reactive. And if you have in the laboratory managed to get them, they should be stored isolated from air, otherwise they will react. alkaline earth, the next row here, and they also are very reactive, but they a bit less reactive than the alkaline metals. Well, they react with water, form hydroxides, release hydrogen. Reactivity increases in the group as you go down because the electrons are less tightly bonded with the core, positive core, because they are further from the core. Okay, so there's applications, fertilizers, things like this. Many applications. Transitive metals. Next here, the blue group. So there's compounds now with more than one oxidation number. That means that they can donate 1, 2, 3 electrons. The chemistry here is a bit more complicated. We are not gonna go deeply into that. But they have a partially filled d orbital. With more than one oxidation number, chemically versatile. They are good electrical and thermal conductors. High melting and boiling points, and many compounds of transition metals are colored. This is also a bit complicated chemistry. Maybe some of you have already studied this somewhere. Iron, copper, gold. Yeah, here's something a little bit explained of the coloration of transition metal compounds. You can read it through if you're interested. Maybe it's not really, it goes already a bit beyond the course content. And how you form the colors of light, how you get different colors. Maybe you already looked into this in the physics as well. Okay, then lanthanides and actinides. Two groups of elements that are located at the bottom. They F block, so it's the F orbital filling. Usually white silvery metals, soft, easy to melt. They are chemically similar and often also have oxidation number of 3. Actinides, radioactive, have many oxidation numbers. What can we say about that? Well, here is the uranium that's been used in the nuclear power plants as to form energy, to form two lighter cores and release energy, big amounts of energy. Okay, so then back to boron group. Starts here from the top again. Well, there's the 2p orbital filling, and it starts with the semi-metal. So boron is a semi-metal, and there's many important uses of these chemicals again. Glass, ceramics, then you have aluminum, that's very lightweight. Durable metal, widely used and quite like common on the earth. Gallium, electronics. So the elements of the boron group have 3 outer electrons, and that's what they, react with, give in the reaction. Carbon group 4 on the outer, 4 reactive electrons, 4 electrons on the outermost shell. And there is carbon, silicon, germanium, tin, lead, very commonly known elements. And also some synthetic element. Yes, covalent bonds together with each other, oxygen group. Again, hey, I'm missing one group here. So I was in carbon group and now I'm already in the oxygen group. I'm missing one group in between. Well, what can you do? There was the nitrogen group. Okay, oxygen group, you have already 6 outermost electrons. And these are very electronegative. They like to react with, for example, metals, or then for example, gas. Oxygen forms this oxygen gas. We already talked about that earlier. Halogens, 7 outermost electrons, highly reactive, and they definitely want one more to have the noble gas structure, electron configuration. And many uses. And these are the things that you then will do the element presentations of. You choose one element and tell a bit more about it. Noble gases. So this is what everybody wants. They are the cool guys and they have the good electron configuration, which is actually the most energetically favorable. Everybody wants that, and that's why they react with each other. But because these guys already have it, they don't have to react with anybody, and then they usually are in this kind of inert gases. Full outer electron shell. Gases at room temperature, and they are also used in many things. You can use as a shielding gas. This means that you have a gas that doesn't react with anything. Okay, so then the nuclear charge, it refers to positive charge of the nucleus of an atom due to the number of protons. Okay. So hydrogen would have +1 because it has only 1 proton, but oxygen already +8 because it has 8 protons. And the electronegativity, it describes the ability of atom to attract the electrons in a chemical bond or electrons to the core. And of course, this increases when the charge of the core increases. And in where is this? Okay, this is, sorry, again in Finnish. So electronegativity in a period to the right, it increases. Where is here the nuclear charge? Well, yeah, there are many things, these arrows here. Atomic radius, of course, increases when you go down because you have a bigger atom. Atomic radius also increases when you go left because the outermost electrons are further because there's less nuclear charge basically to attract them to the nucleus because they are on the couple of electrons on a different electron core, they are further. Metallic character, so that means that you give the electrons away. It's here in the left. And then also when you go down, because the electrons are further away from the nucleus, Non-metallic character, on the other hand, increases to the right and to the this corner. Yes. These things aren't so, these get a bit, maybe a bit specific for the course. There's about atomic radius, what I already said. Okay, electron affinity, the amount of energy released or bound when a single electron joins an atom. If electron affinity is negative, energy is released, and if positive, energy is being bound. So electron affinity, the amount of energy that you get when you put one electron to the atom, of course, increases here because these ones actually want the electrons. And here it decreases because these ones want to get rid of the electrons. Ionization energy. Energy required to detach an electron from an atom or molecule. So here it's difficult to take the electron out. These ones really want the electrons, and here it's easier to take it out. And of course, when you go down, it's, the electrons are more loosely bound, and you get one electron of the nucleus of the atom easier with less energy. Did I jump? Metallic character. Okay, yes, this is something that we already talked about, and non-metallicity or non-metallic nature, this also. Okay, so then we go a bit further, and why does a chemical bond form? So the chemical bonds are created because atoms tend to achieve more stable energy state. So we had 118 different kind of atoms, but we have like millions of compounds. So these atoms want to react with each other, and of course those atoms that are not noble gases, they want to have the outermost electron cell full, or on some other way a more stable energy state. And this stability is achieved when atoms share or transfer electrons in such a way that their outer cell, over here, the same fills, or then at least they get some kind of a more energy efficient state. So atoms tend to reduce their energy to the lowest possible level. By binding to other atoms, they can reach a lower energy state than when they are alone. Also, then there's this octet rule. Many atoms tend to have 8 electrons in their outer shell. And this is how they are more chemically stable. And this can be achieved by sharing electrons with covalent bonding or by transferring electrons with ionic bonding. And positively and negatively charged ions attract each other to form ionic bonds. Also, electrical attraction holds the ions together, and you get a stable compound. While in covalent bonds, the atoms share electrons. So, yeah, chemical bonds are really, and of course, central in all the chemistry, and these are achieved by chemical reactions happening. Types of chemical bonds, this that we already mentioned, there's ionic bond. So a metal atom donates electron to a non-metal atom, although it's here marked like they would share them. But it's actually here the sodium gives it to the chlorine, and then they are bound together because the natron would have plus charge, chlorine minus charge, and they have this electrical attraction. Covalent bond, non-metal atoms share electrons. So the non-metal atoms tend to share the electrons. They are actually staying on all of their the outermost electronic shell, and they are happy. They get either the octet or at least the full electron core. Metallic bond, this was already mentioned, electrons move freely between atoms. Then you have also this hydrogen bond that's been mentioned here, which bonds then the water molecules, these kind of molecules together because of a bit weaker electric attraction. Or van der Waals forces, this electric, even if you would have a completely like chargeless covalent compound, you have still some kind of small forces of the electricity appearing there, like because this electricity is not stable in one place all the time. How to say it? A weak forces that arise between instantaneous dipoles. You get an instantaneous dipole. These are important in intermolecular interactions, however, even if it sounds a bit like instantaneous. Okay, metal bond, bonds between metal atoms. Again, we talked about this. So these metal atoms are nice to each other, and they like to donate the outer electrons to a common electron cloud. And this moves freely around the atoms. This electron cloud binds the positively charged metal cations together, and this is a strong bond. But then they have a number of properties. So they have this electrical and thermal conductivity, so the electrons move freely there. They can easily then transfer electricity and heat through the metal. Yeah, and then also they have metallic luster, and this is to do with excitation and return of electrons to lower energy levels, and they emit light. So this emits this light radiation, shiny surface. And then there's this malleability and malleability. There's twice there. Free electrons allow metal cations to move past each other, so it won't break the structure if you hit it with a hammer. You can make it into different kinds of forms. Metals tend to be hard but malleable. Iron, copper, aluminum, and here is some kind of example still. So if you would have sodium, you have only one electron to share. Magnesium already 2, aluminum 3. And this so is also the charge of the atom then changes there, depending on how many electrons you gave to the common purpose. Then a covalent bond, chemical bond. 2 atoms share electrons. Well, this is something that we already had somewhere, but here it's still the same thing. Iodine shares 2 electrons, so it's a single bond. Oxygen, 2 pairs of electrons, double bond. And nitrogen, triple bond. Triple bond is the, this is the maximum amount of electrons to be shared. And then you can have polar bond. Electrons are unevenly distributed between atoms, resulting in partial charges, for example, in water. So the oxygen is more electronegative than hydrogen, and it takes the electrons more to itself. It's a bit more selfish. Then, covalent compound. So when two or more atoms share electrons with each other to form covalent bonds. So non-metal atoms, these can be simple molecules, but they can be also more complex structures. Water is simple carbon dioxide, methane, but then you can have this, like big long chains, like with carbon. To have here, well, here is more examples of molecules. So there's oxygen, carbon dioxide, water, and there's the little partial charge marked. DNA also really, this is also a molecule, basic molecule of life that contains our genetic information. And there's a huge amount of atoms and really long and big molecules with all sorts of complicated structures. So these are also covalent bonds between non-metal atoms. Ionic bond. One atom donates an electron to another atom, creating positive and negative ion. There's electric attraction between these ions that hold them together. For example, our table salt, sodium chloride. This is what we already talked about. So in solid form, these kind of ionic compounds don't conduct electricity, but when melted or in aqueous solution, where ions can move freely, it conducts electricity. So there you have positive and negative ions simmering and swimming, and then they can conduct electricity. Ionic compounds are hard, but they break easily if you hit them with a hammer, because the ionic levels can slide past each other, and ions of the same brand. Oh, that's not great translation. Same charge, they repel each other. So if you get two negative or two positive atoms next to each other, then there's a repellion and this structure breaks. Oops. Okay, I think this is the next, yes. Ionization is the process by which electrically neutral atom or molecule loses or gains electrons. So you get cations and anions. Anion has negative charge and it has more electrons than protons. So it got an electron from somewhere, or even more than one. And a cation is positively charged because it has more protons than electrons, so it has lost for some reason some electrons. And here we had an example, for example, with the natrium chloride. So the natrium didn't want it, and the chloride did. So in the periodic table, you always have the neutral atoms, but then when they start interacting with each other, you can form cations and anions by loss of or gain of electrons. An ion is negatively charged. Ion that's formed when atom or molecule receives one or more electrons. So an ion can be also like a bit more complicated. So you can have elements that are bound to each other, for example, with covalent bonds, sulfide ion, and then this compound is negative. So here's only the chlorine. Chlorine here is negative because it gained 1 electron. Now it's happy because it has full outer electron shell. This is the energetically more favorable state. Cations, yeah, cations, then they lost their electrons. For example, calcium, natrium, they wanted to lose. Then they have again full outer shell. So this is more energetically favorable state. And then you can have also more complicated cation, for example, an ammonium cation. So there's again stuff bound to each other, but lack of electrons. Ammonium ion. That's it. Okay, then that wasn't all though. There's another oops, slideshow that I should still go through. Oxidation numbers, stoichiometry, amount of substance. Here's just a little bit of this, and then in the exercises we will be calculating with this information. What these things mean. So the oxidation number or oxidation state describes the transfer of electrons in an atom. So you can mark it even in a covalent compound like water, so that these electrons shared here with oxygen and hydrogen would be actually the oxygen would have them because it's more electronegative, and the hydrogen would have lost them. This is how you can mark sometimes this is something that you need to do. This is how you can mark oxidation number. And in certain substances like transition metals like chromium, you can have many different types of oxidation numbers. So it's a metal and it wants to give away the electrons, but it can give away either 2, 3, or 6. The 6th one is, I think, toxic or carcinogenic. There was even a movie about this, where people in the America had some problems with some factory that had released this into the nature, and then the people had got cancer in that place, and then this was taken into the court, these cases, by somebody who realized that this is happening. Then you can have different kinds of colors with the substances with different oxidation numbers. Oxidant is an oxidizer, substance that causes another substance to oxidize in a chemical reaction. So it has the ability to receive electrons from another substance, and this leads to an increase in the oxidation number in the oxidizing substance. Oxygen is the most common oxidizer used in many combustion reactions. So it's actually the combustion can be also taught as oxidation, or hydrogen peroxide or potassium permanganate, nitric acid. Combustion reaction here as an example. Well, we will be talking about this later, and we already talked about it. Reducing agent. So the reducer donates electrons to another substance, and it leads to decrease in oxidation number. So for example, hydrogen wants to give the electrons away. It can be used as a reducing agent, or coal, or natrium, sodium, or aluminium. Okay, let's see chat. Okay, I put this already, I put this as 2 hours for today because of the amount of the, because I couldn't do it the last week. So I'm gonna anyhow talk this through because somebody has to watch this later. Maybe somebody watches this later as a record because there were only 2 of you present anyway. But if you have to leave, there's not much you can do. Then we can continue with the calculations next week, and I will still continue the lecture. But you can go if you have to leave. Okay. Okay, so there's still a couple of things to go through on this lecture that I have to, well, I guess, talk about. There's a example of blast furnace. For sure, you will be talking about this later. Hmm? Okay, thanks. Yes. So I will still mention the stoichiometry of the reactions. Stoichiometry in the reactions is this actually the how you balance the chemical reactions, and this is something that we will now have to start practicing or already in the first calculation exercises. So you have the chemical formula of a substance, and or you have some elements and you form a product, and you have the balance so that you have the same amount on both sides. And the amount of substance where you use the symbol N is the basic quantity in chemistry and physics, and that expresses the number of particles in the object under consideration. The unit used is the mole, which corresponds to the number of particles according to the Avogadro constant. And the Avogadro's constant is this huge amount of particles. So it's something like 6 times with 10 times 10 on the power of 23. This is how many particles are always in a mole of a substance. Large counting unit for particles. And this is named after Avogadro, who has proposed that equal volumes of gases contain equal numbers of particles, which is Avogadro's law. And the actual value of this constant was determined much later by experiments, because this was already, this Avogadro was working as a chemist or already in the 1800s. So where does the Avogadro constant come from? It's determined by measuring the number of atoms in a known mass of pure substance. And you can use X-ray crystallography or electrochemical measurements. And this is the amount anyhow of the particles. And you can now convert between grams and number of particles. And this is what's been done in the chemistry calculations. And here are some, so the Avogadro constant linked to the molar mass. So amount of substance in moles is mass divided by molar mass. And molar mass is, of course, how much 1 mole of some substance, which was this huge amount of particles, that how much that weighs. And that you can find in the periodic table or in the equation book. Molar mass, the mass that 1 mole has. Atoms, so molecules or other basic units. So this can be the atoms, but it can be also molecules, the same amount, the Avogadro constant of molecules. So for example, for water, you can calculate it when you know the molar masses of hydrogen and oxygen, because you know that there's two hydrogens. You multiply the molar mass of hydrogen by 2 and 1 oxygen. So you take the molar mass of oxygen, you add them together, and you get the molar mass of this compound called water. And here are still some examples of the calculations. And this kind of calculations we will then calculate throughout the course, and even something a bit more complicated, but now in the first calculations exercise is something like this. Here is even more examples. You can go through them. That's it. Okay, thank you, and see you next week in the calculation exercises. Hope you're all present there.